For those we've already experienced, climate change is essentially like pouring salt into a large wound that we've already created for ourselves. We've put ourselves in vulnerable places. We've paved over paradise and put up a parking lot, no place for the water to go. We've got lots of flooding because of the policies that we've basically, agreed to over this time. So we have to understand that. But in the future, I view climate change as sort of the 800-pound gorilla in the room that's forcing us now to do the things that we know we should have always been doing along the way.
I am honored to introduce our speaker for tonight's forum, Dr. Ellen Douglas, Associate Professor of Hydrology at the UMass Boston School for the Environment. Dr. Douglas's research interests include evaluating the impacts of climate change on New England hydrology, assessing the vulnerability of coastal communities to flooding, improving methods for sustainable water resource management, and monitoring the performance of river restoration through dam removal. The news has been filled these last couple weeks about the impacts of hurricane season on our Atlantic and Gulf coasts, and we know that you are all primed and excited to learn about the vulnerabilities and concerns for our own beloved coastline, and most importantly, what we can do about it. It's my pleasure to welcome Dr. Ellen Douglas.
Let's get to it. So, you'd think we'd planned this to occur this fall. It's very timely, but we actually have been working on this. We planned this actually last May. So, and we just decided to have a little extreme event for you to make your way through, just to put an exclamation point on the topic. So here we go. So, we all have heard that, the temperature is rising. And we also hear a lot about record events. Every time you listen to the weatherman or the weatherwoman on the TV, you hear talk about unprecedented events, record events. Well, theoretically, records will always be broken, but typically what happens is the time between record events should get longer and longer and longer. But climate change is actually doing just the opposite. The 15 of the last 17 years have been the warmest year on record. And 2016, last year, April was the warmest April on record. And not only was it the warmest record on record, but it was the warmest by a large amount, half a degree Fahrenheit, which when you're breaking a record, it's usually by a little bit. That was by a lot. And then July of 2016 ended up being not only the warmest July on record, but the warmest month on record ever. And then 2016 for the whole year ended up being the warmest year on record. And so we keep hearing the same thing over and over again. And I just want to illustrate that point with this little YouTube clip. And what it's going to show is, I'm going to pause it for a second. So what it's showing is global temperatures that we've measured in different manners from the late 1800s through through current times. And you'll see these colors. The blues are temperatures below average. So, you're looking at the long-term average, and blue is temperatures below average. And then as you see things get into the red, that means temperatures are above average. So this was put together by NASA, and I thought it was a nice little illustration. So notice how the temperatures in the northern latitudes are really, really much higher than average. And I love NASA's new logo. The planet's changing, we're on it. I love that. So anyway, let's go back to our talk. So you hear a lot of talk about this changing temperatures. Isn't it all just natural climate variability? Well, we actually have a lot of records that show that what we're observing now is really outside of what we've observed in the past. This is a record of climate for the last thousand years of global temperatures in the northern hemisphere. And you can see there's one trace here, the blue trace, that shows the medieval warm period, and then the little ice age. A lot of people will say, well, we're just recovering from the little ice age. But that actually was a fairly regional North Atlantic effect. When you look at the red and green traces, you see that the temperature was fairly stable over the last 100 years until you get to the middle of the 1800s and the early 1900s, and suddenly it shot up. And we have other records that show this is actually a trace of temperatures and CO2 concentrations, actually, which are related to temperatures that go back almost 1 million years. And you can see by that red line, it goes up and down. We do have natural variability in the climate, but in the last almost million years, the CO2 concentrations in the atmosphere never really went above 300 parts per million, and now at this point we're at 400 parts per million. And of course, according to the projections, things could get much worse in the future. So we know, based on the observations that we have, that what we're seeing now is not only in high temperatures, but they're increasing at a rate that hasn't been seen in the past. So what we know is that the climate is changing and that humans are the predominant cause. So the Intergovernmental Panel on Climate Change in 2013 stated that the warming of the planet is unequivocal, and that it's extremely likely that since 1950 this warming has occurred. The warming that's been observed is due to human activities. And when the IPCC is actually a fairly conservative, they don't like to overstate things, and so when they use words like unequivocal and unlikely, they assess a probability. So unequivocal means that we're 100% certain. Extremely likely means that they have greater than 95% certainty that what they're saying is true. And so you can really rely on the expertise of these scientists and believe that they really know what they're talking about. They're not alarmists. They're actually stating what the science says. Now, how do we know this? Well, we know this because there are many groups that have built these climate models, these models that simulate all the processes on the planet to the best that we understand them. So they simulate the interactions between the ocean and the land, and the ocean and the atmosphere, and the land and the atmosphere. And we have these big Earth system models. And we run in order to know what is causing these temperatures increases, we run different factors that we know could be the cause and see which actually reproduces what we've seen. So I wanted this is the only other link that I wanted to share, but Bloomberg put out a really great series of graphics that illustrates this really nicely. So I wanted to share that with you, and you can if you Google Bloomberg global warming, you can find this yourself. So this is a trace of our average global temperatures since the late 1800s. So that's the observation. And then these global climate models, then you can run different factors through them to see what might be the cause of this increasing temperature. So some people say, well, is it the changes in the Earth's orbit? Well, we know the Earth's orbit changes. But if you run just Earth orbit through the model, it really doesn't reproduce what we've seen. So is it changes in solar radiation? Well, that does cause little variations, but again, nothing near what we've observed. What about volcanoes? We know volcanoes have a big effect on global temperatures, but it turns out when we have volcanoes, like here this is Krakatoa, and I think this is Mount St. Helens, it actually causes a cooling. So it's not volcanoes. So if you put all those natural factors together, you can't reproduce the temperatures that we've seen. So what happens then if maybe it's deforestation, maybe it's other human activities? Well, actually if you only have deforestation, that should actually cause a cooling in global temperatures. What about ozone pollution? So you can see how scientists can run with these Earth system models, you can run all these different factors in there and see what it is that causes the warming that we've observed. It's not ozone pollution. What about aerosols? So if any of you have been to Southeast Asia or South Asia, there's a lot of biomass burning. You see all this smog. That actually causes a cooling. So that factor isn't causing the warming that we've seen. So what about greenhouse gases? Greenhouse gases, you run those alone through the model and you start seeing an increase in temperatures like we've been observing. So if we put all of those factors together, All of the factors together, solar changes in solar radiation, changes in Earth orbit, deforestation, volcanoes, suddenly now you can reproduce this observed temperature that we've seen, and the main factor that's driving this warming is CO2 and greenhouse gases. So that's how we know that this is occurring. So what we're doing is we have this, if any of you are old Star Trek fans, you remember they often said we're carbon-based life forms. Carbon is everywhere. It's a part of life. Carbon is what puts the org in organic. So we need carbon in order to be alive. And so there's carbon in everything. There's carbon in the atmosphere, there's carbon in the soil, there's carbon in the water, there's carbon in trees, there's carbon everywhere. And there's this beautiful big global carbon cycle that now we're taking fossil fuels, which is carbon that has been buried deep in the earth. We're taking it out of the earth. It's been separated from this carbon cycle, and we're adding it to the atmosphere and imbalancing this carbon cycle. So that's what's causing, with that excess CO2 going into the atmosphere, is causing the planet to warm. And it doesn't look like, so far, our emissions are really changing all that much. These traces here are actually projections in the future that the IPCC made, and this line here is actually observed emissions up to 2010, and you can see we're kind of following the highest projections that were made back in the 2007 report. So we're still pumping more CO2 into the atmosphere and imbalancing that beautiful large global carbon cycle. So what does all this have to do with extreme events? So now you're just going to get a little tiny bit of statistics, but don't freak out, not too much. So when temperatures are measured, it's data, right? We collect all these data, and if you collect enough data, they begin to develop these bell curves that I'm sure you've seen. And so this represents the distribution of temperatures, and most of this high point means most of the temperatures fall in this range. So when the weatherman says it's above or below normal, what he or she is talking about is above or below that average value in the center of that distribution. And we have usually at the upper end and the lower end of these distributions, we have what we call extremes. So at this point, there's a temperature that we call a hot extreme, like say 90 degrees Fahrenheit here in New England. And here we have a cold extreme. So those have low probability, maybe a 5% chance of occurring in a year. But that's a threshold that we call a cold extreme and a warm extreme. So under normal conditions, you'd expect to get that extreme once, in 5% every year. So what happens if you take this distribution of temperature observations that we've made and you just shift the mean of the average up a little bit? So you move it from where it was located to forward. So the average, you're not changing the shape of how the distribution happens, you just shift it upwards. So then what happens to the extremes? So now the cold events don't happen, the probability of the cold events happening drops, but the probability of these extreme warm temperatures increases quite substantially. So that's how an illustration of how a shift, even a small shift in that mean value, that average value in the middle, can really affect how those extreme events occur. Same thing with precipitation. The precipitation distributes differently. Most of the time it doesn't rain, so you have a lot of values near zero, and then you have some extremes at the tail end. Those really heavy rains, like you actually walk through here to get here, that might be something that falls in this range of the distribution. So when you change that distribution, you actually increase the probability of those precipitation events of occurring. And this is just an example from Europe. I don't know if any of you remember, but in 2003 there was a massive heat wave that occurred that killed thousands of people who were vulnerable. And so this shows actually observed data falling in this distribution. So most of them fall in this around the average value. And then 2003 is way, way out in the extreme. So that's just an illustration of one set of observations of how we expect this shift in the average value to really affect the extremes. So the IPCC put out a report and stated very clearly, small changes in the average value result in larger changes in the extremes, and a changing climate can lead to changes in the frequency, the intensity, the distribution, the duration, and the timing of these events, and we can expect to see unprecedented events. So how many times have we seen unprecedented or heard the word unprecedented when we're talking about these weather events? When they were forecasting Harvey, the National Weather Service came out. Now the National Weather Service they're not alarmist, right? When they come out and say this is unprecedented, the flooding and the rainfall that we're going to get is unprecedented, you really have to listen. And they were right. So we have, when these big events happen, then we get these presidentially declared disaster areas. And this is a graph showing the blue is the U.S. Disaster declarations over time, and the red is those occurring in New England. Now, the New England scale is a little exaggerated just so you can see, but in both cases, you can see there's been an increase in these declared disasters since around the 1980s, especially since the 1990s. If you put them both on the same scale, you can see that we've had a doubling from the 70s through the 70s and 80s. These are the average number of events over the time frame. So it doubled here and then it doubled here again. Same thing in New England, even though we experienced fewer events that went from 1 to 2 and then 2 to 5. So we have seen an increase in these events. So why is this? Is this a climate change signal? Well, let's investigate that a little bit. So NOAA categorizes these storms based on their cost, and they have a whole data set about what they call these billion-dollar disasters. And so a disaster like Hurricane Harvey, or probably will be Irma, would be considered, would be lumped into this billion-dollar disaster category if the damage costs actually exceed $1 billion. And you can see that there are a number of different kinds of event that cause a lot of losses, but tropical cyclones by far cause the most amount of damage, either on an aggregate basis or even on an event basis. So tropical storms are the ones that really cause us the most damage. Now this was a New York Times article that was put out last week, which I love journalists because they have the most clever ways of displaying data, boring data. Like I just put it in a graph, and then the journalists, they come out and they put out something beautiful like this that really tells the story. So these bubbles, the colors are based on the different types of disasters. So the dark blue are hurricanes, the green are severe storms, these kind of tealy colors are floods, and the yellow are droughts. And then the size of the bubble is the cost. So you can see hurricanes that have occurred. So this is since 1980. So that's only 30 years. It's not a lot of time, but it's the time that we've been collecting these billion-dollar storms. So all of these are billion-dollar events. So this is Hurricane Andrew. This is Katrina. Katrina was the record damage. It was the biggest costing storm until Harvey. It's possible that Hurricane Harvey that we just experienced at the beginning of this month could even exceed the cost of Hurricane Katrina. So, it seems like something's going on here. So what's going on? What's the cause of these large catastrophic events and the damages that come along with them? So before we talk about that, let's talk a little bit about how a hurricane forms. It turns out that it takes a lot of things have to come together in order for a hurricane to form. First, you have to have sea surface temperatures in the tropical ocean to be above about 80 degrees Fahrenheit. And coincidentally, or maybe not so coincidentally, in September, the largest extent of this warm sea surface temperature occurs in September. So it's no surprise then our peak hurricane season is in September. You also have to have atmospheric conditions that support thunderstorms. So thunderstorms will develop over Africa and they'll march their way across the tropical ocean, and they act like little seeds for these hurricane events. You have to have high humidity in the troposphere. These thunderstorms have to be, or these events have to be about 300 miles away from the equator, so there's enough Coriolis effect to start it spinning. And then you have to have what's called low vertical wind shear. In other words, the winds aloft and the winds at the surface can't be very different. If they do, then it tends to rip apart hurricanes. So you have to have low vertical wind shear. So those are all the conditions that have to occur in order to have a hurricane form. And so in September, we're used to seeing some of these hurricanes form, but they don't all turn into massive storms, and they don't all hit land, hit our land. Another thing that I found out when I was doing a little research for this is one of the things that makes a hurricane go from a small hurricane to a big hurricane is it has to move over this warm temperature, warm water for a long time. And in the Caribbean and the Gulf of Mexico, there's this thing called the loop current. Now, I'm a hydrologist, I'm not an oceanographer, so this was all new to me. So this loop current actually, sometimes it goes way up into the Gulf and sometimes it doesn't. But in the case of Katrina, which obviously was a large hurricane, the loop current actually came way up into the Gulf of Mexico, so it gave it that long path of warm water over which it traveled to cause the strengthening. And also sometimes this loop current, this bubble here actually breaks off into an eddy of warm current in the Gulf. And so Hurricane Rita, that then followed Katrina, had this pocket of warm water in the Gulf that caused it to strengthen. Turns out that Harvey, that we experienced just a couple weeks ago, also we had a bubble of this warm loop current that broke off and allowed it to intensify over the Gulf. So you have to have all these really unique events come together, and sometimes, sadly, they do, and cause the disasters that we've seen. So why are these, then, knowing that it's such a unique event that occurs in order for these hurricanes to even develop and then become these massive hurricanes like we've seen, why are these hurricane-based disasters becoming more costly? Well, as any good scientist will tell you, it's complicated. It depends. But on the one hand, we've gotten much better at actually tracking hurricanes, and we all love to watch, or I do anyway, love to watch the weather forecast and go to the National Hurricane Center and see the little spaghetti plots where they have like the 40 different hurricane models, and you can see where they're all telling you where they're going to go. And as the event gets closer, those spaghetti models begin to converge so you can see the track where it's going to go. We've gotten better at tracking hurricanes, but unfortunately, because the development of these hurricanes and the intensification of these hurricanes is so complicated, we really haven't improved our ability to tell how much they're going to strengthen and when they're going to strengthen. So Harvey actually was just this sort of unorganized mess around Florida a few days before it turned into a massive hurricane and hit Louisiana. So sometimes they can surprise us. Another impact, another issue in these disasters is that there's just more of us living in vulnerable places, and we have more stuff. So we're living in these areas that are vulnerable to hurricanes, and we have more valuable property that gets damaged. So global population exposed to hurricanes has gone up 3 times since 1970. And this study here by Pilkey et al. Took into account the fact that we've had population change and increase, and we've also had increase in wealth, and took that all into account and found that the per capita wealth in the U.S. has increased by about 50%, 1.5 times. So basically, we're putting ourselves more in harm's way, and we're making more valuable property where we're living. So this is a graph from that study that shows the population in coastal communities in the U.S., and this is in the Northeast. And so it's no surprise, New York, New Jersey have always had very dense, high population areas. But here's Florida. So the dark is 1930, and then the gray is 1990, and then the medium gray is 2005. Here's Harris County, Texas. And here is Florida. So in the last 40, 50 years, a lot of people have moved to these areas that are vulnerable to hurricanes. In fact, the population of Harris County, Texas, now this was written back in 2008, so it was long before Harvey. The population of Harris County, Texas has grown 3 times since 1960. So lots of people moving into areas where hurricanes are a threat. So when these researchers looked at those billion-dollar storms over time and took into account, basically controlled for changes in population, changes in wealth. They really didn't find any trends in the storms that were due to the storms. The increase that we see in that graph that I show is because we're putting ourselves in harm's way more often, and we're developing in ways that are causing us to be more vulnerable and to have more stuff that's at risk. But in the future, the story could be different. Now, this is this whole idea, the whole topic of how hurricanes are going to be affected by climate change is actually quite a fascinating debate in the scientific literature that I've been reading for at least the last 10 years. There are two groups of thought. There's one group of hurricane experts that believe that, hurricanes are cyclical and they're complex and they're impacted by a lot of things, and climate change isn't necessarily the main driver. And then there are others who know that some of the processes that cause hurricanes are actually impacted by climate change, and so we can expect to see more powerful hurricanes. So Carrie Emanuel over at MIT is one of the ones who does a lot of simulation on hurricanes in the future, and this is all these nasty spaghetti graphs here are basically showing storm surge from hurricanes. This is actually Tampa, Florida. Again, it was written before, well before Hurricane Irma came through. But these are different climate models, climate change models, simulating the impacts of storm surge from hurricanes in Tampa, Florida. The blue is the current state, so you can expect, and this is actually the return period, the 100-year storm, 1,000-year storm. So as the risk increases, so does the storm surge, or I should say the opposite way. As the storm surge impact increases, the risk, the number goes up. So you can see in all cases that from the current state to the future state, we're going to see more storm surge impacts. And the models have different shapes of their curves, but they all say that we're going to be impacted more, that we're going to see larger storm surge impacts, events in the future than we are now. And so that's not good news. So let's talk a little bit more about New England. So we know, we know Tampa got hit by Irma, and one of the biggest impacts of the whole west coast of Florida was storm surge. So this is a very relevant paper, and hopefully they're thinking about this as they're recovering and thinking about how they're going to move into the future. So let's talk a little bit more about extreme events in New England. I happen to like to sort of keep track of these things. So in 1996, we had a big storm that caused a lot of inland flooding, and it turned out to be the record precipitation event in many of the stations in northeast Massachusetts. In October 2005, more flooding, more rainfall, more flooding. May of 2006, we had the Mother's Day storm, caused a lot of inland and coastal flooding. April of 2007, we had the Patriots' Day storm. For a while, it looked like we were going to have extreme events on holidays, which I guess was a little convenient. And then probably all of you remember the ice storm of December 2008. Typically when we have ice storms, they impact a very small area, but this was actually very extensive throughout New England. There was like almost 700,000 people out of power for a while. In February 2010, we had the snowicane. The snowicane was a nor'easter blizzard that actually had hurricane-forced winds, very unusual in the winter. March of 2010 was a real record breaker. We had 3 consecutive weeks. Does anybody remember March of 2010? We had 3 consecutive weeks of extreme rainfall that by the end of the month, it just saturated all the watersheds, and we had all kinds of flooding. And it also turned out to be, March 2010 was the wettest month on record at the Blue Hills Observatory. Not just the wettest March, but the wettest month ever. It exceeded the previous record, which was from Hurricane Diane back in 1955. Then in August 2011, we had Hurricane Irene. At first, the trace looked like it was going to go right over Massachusetts and New Hampshire, but it took a sudden veer west and went over Vermont instead. And a couple months later, we had the Halloween blizzard, or the Snowtober, where it was October 30th. There were still leaves on many of the trees, and we had a big a snowstorm blizzard, caused a lot of damage just because the trees weren't quite ready for snow yet. And that winter of 2011-2012, ended up being the driest winter on record. And February 2012 almost would have been the driest February on record, except it was a leap year and we had rain on February 29th. Dang, so close. But then we all remember Superstorm Sandy. So Superstorm Sandy was actually a hurricane that came up from the tropics that kind of blended with, it was called a superstorm because it blended with an extratropical storm and intensified. It became stronger because it went over unusually warm waters in the Atlantic. It had a record low barometric pressure at the center, and it had record storm surge when it actually made landfall. In New York City, Sandy, the max surge hit right at the astronomically high tide. So the worst possible time for an extreme storm surge to hit is at the highest high tide, and that's when it hit in New York City. Here in Boston, we were lucky. It happened very close to low tide. So we have a 10-foot tide range here. So the storm surge we had in Sandy in Boston was just shy of 5 feet, which is a pretty good storm surge. But because it happened at low tide, we almost didn't see it. So it caused a little bit of flooding around the New England Aquarium here and along the coast, but we really didn't see much of an impact from Sandy when it came to flooding. We had a lot of wind. We were 600 miles away and we had a lot of wind. I was very impressed by that. We saw some flooding around Long Wharf in this area, but if that had happened, if Superstorm Sandy's storm surge had happened at high tide like it did in New York City, this is more like the flooding we would have seen. So we would have seen a lot of flooding in South Boston, on Atlantic Avenue, over in East Boston, Charlestown. So we really dodged a bullet with Superstorm Sandy, and so it really made a lot of people in New England, and especially in Boston, realize, okay, we need to do something. We need to really accelerate our preparedness. So what does this all mean about the future of coastal storms in New England? So hurricanes happen in New England. They happen in the South much more frequently than they happen here. We get, on average, a hurricane through once every 3 years or so. The intensification or strengthening of hurricanes, the processes that go into this are very complex and not perfectly understood by science. And so there really is no scientific consensus at this point on what the impacts of climate change is going to be on hurricanes in the future. But there's a fascinating debate going on between these two different camps, as I told you, as to what the future could look like. But Carrie Emanuel at MIT has found that there's a real strong link between sea surface temperatures and what he calls the destructive power, the power dissipation index, which indicates the destructive power of hurricanes. It's related to sea surface temperatures, and we know that sea surface temperatures are going up because of global warming. And so he's a firm, he does a lot of modeling to show that even if the frequency of hurricanes, of all hurricanes, isn't changing, we're going to be seeing more intense hurricanes in the future because of climate change. The thing that really impacts us here, the thing that causes our extreme events in New England are the nor'easters, or the extratropical storms. These have a bigger influence because in Boston Harbor is sort of open to the northeast, and you got these nor'easters coming in from the northeast, so it's like waiting with open arms as these storms come in and the storm surge. And they also happen more frequently. So we get 2 or 3 big nor'easters a year. So, and they last longer. So they have a more dramatic impact. But nor'easters, the extratropical storms, are much harder to classify. I mean, you can see a hurricane, right? And when it's really intense, you can see the eye and everything. But nor'easters are harder for meteorologists to classify. And so there hasn't been a whole lot of research on them, but it is now an active area of research. So from what has been done, what research has been done so far, there isn't evidence that says that these extratropical storms are increasing in magnitude or frequency. But there is some evidence that says we're seeing a northward migration in these storm tracks. And there's also some evidence that the season that we experienced these extratropical storms is actually expanding. So used to be nor'easters always happened in the winter, but now we're beginning to see some of these large extratropical events happen in the fall time and in the springtime. So there are impacts, but this is an area of active research. One researcher that I found when I was doing a literature review totally ignored the whole debate over whether or not hurricanes are being impacted and just looked at the storm surge from these storms. So they looked at storm surge along the Gulf and along the East Coast to see if they could see any trends that they could attribute to climate change in that. And they found that there was a relationship between storm surge and global temperatures and sea surface temperatures, and that over the 20th century, there's actually been a doubling of what they call Katrina magnitude storm surge. So these events that cause big storm surges have increased have about doubled over the 20th century. And then using future projections from climate models, they projected that under a 1 degree centigrade warming, that we could expect to see anywhere from 2 to 7 time increase in these storm surge. So regardless of what's causing that storm surge, we can expect that if you along coastal areas on the Gulf Coast and the East Coast of North America, we can expect to see larger storm surge events. And we know from watching the devastation that occurred in Florida from Irma, that storm surge is often the thing that you worry about most in these hurricane events. So what does this all mean? What does climate change mean for Boston here? Well, I was a part of a team that worked with the city of Boston on what they're calling Climate Ready Boston. And we brought together, and if you're interested, so there's a pretty extensive and well-written, I might say myself, a well-written report that explains all these impacts pretty well. You can go to climateready.boston.gov and read the details. I'm just going to give you some highlights from that. We brought together teams of scientists from around Boston and the region to look at the 4 major impacts that we feel that Boston has to worry about: sea level rise, coastal storms, extreme precipitation, and extreme temperatures. And I'm just going to give you a few highlights from this BRAG, the Boston Research Advisory Group, the BRAG report. One of those results were that, no surprise, we're going to see more of these extreme hot days. So over the historical record from 1971 to 2000, we've seen about 11 days above 90 degrees here in Boston on average. So if we, in the future, as the climate continues to change, we could see anywhere from 20 to 40 days in the near term, 2030, which really isn't that far away anymore. And then by the end of the century, by around 2070, we could see anywhere from a month to 2 to 3 months of days above 90. Now, that's pretty dramatic, and that's a pretty harsh thought, to be living in New England and experience a full summer's worth of 90-degree days or higher. Now, one of so this graph, there's a pretty wide range of these projections, and the reason for that is we don't really know what our CO2 emissions are going to be in the future. So scientists figure, well, let's assume the best case, and let's assume the worst case, and see how much of a range of these projections it leads to. So in this case, if we follow an emissions scenario, so if we stop emitting all the CO2 in the atmosphere that we're doing right now, if we really reduce our CO2 impact by turning to renewable fuels and energy efficiency, we can follow this lower part of the graph here, which would be maybe a couple of dozen more days of 90 degrees above by 2030, and maybe 25 days of above 90 degrees by 2070. But if we continue to pump CO2 at the rate that we are right now, we could see as many as 90 days above 90 degrees. So that's not good news, but one of the good news that you can take from a graph like this is that what we do now in mitigation, if we continue to reduce the amount of CO2 that we pump in the atmosphere, we can have a very dramatic impact on how our climate looks at the end of the century. No surprise, we are going to see fewer cold days As you would expect, remember that graph I showed you? More warm days, less cold days. Well, we'll see that in Boston. But the surprising thing, one of the surprising things I learned from this report is that doesn't mean we're not going to see snowstorms like we saw back in 2015. Those extreme snowstorm events are still likely to continue to occur even as our planet warms, because we know there's more moisture in the air because the atmosphere can hold more moisture. There's more variability because we're destabilizing the climate. And so 2015 was just not necessarily an anomaly. We could see those kinds of extreme winter storms in the future as well. We'll see more rainfall. No surprise there either. Again, the atmosphere can hold more water, so you'll see more extreme rain events. But the thing that we worry about here, I think, a lot in Boston is sea level rise, because we have all this coastal property. We live on the coast. We love our coast. We love looking at the ocean. So we really worry a lot about the effects of sea level rise. So what causes sea level rise? Well, we know that as water warms, it expands. So the oceans are big. So when expansion occurs, the water starts encroaching on the land surface. So during the 20th century, we saw about 1 millimeter per year of sea level rise due to thermal expansion. We also know that a warming temperature leads to melting glaciers. So we saw about 1 millimeter per year of sea level rise over the 20th century because of melting glaciers. Interestingly, as a species, we have pulled so much water out of the ground to irrigate crops and things like that, that there's actually a detectable signal in sea level rise due to groundwater extraction. About 0.5 millimeter of sea level rise over the 20th century is due to pulling groundwater out of the earth and irrigating our crops, and then it runs off into the rivers and into the ocean. That's pretty amazing. And also, because of warming temperatures, we have the large ice sheets that are melting. That's added another 0.6 millimeters per year of global warming, of sea level rise over the 20th century. So during the 20th century, the major component of sea level rise was due to this thermal expansion. The water is warming, it expands, it encroaches on the land surface. However, in the 21st century, we're still going to see thermal expansion. We're still going to see some melting of glaciers, although there's not a whole lot of glaciers left to melt. The big impact is going to be what happens to the ice sheets. So there's a lot of water tied up in these ice sheets, and I'm not saying by any means that all that ice is going to melt, but the fact that another area of active research in climate science is understanding how these warming temperatures are affecting the massive ice sheets we have in Greenland and Antarctica. There's a lot of ice there, and it's going to have a big impact on sea level rise in the future. So ice sheet melting and ice sheet dynamics is really going to be the big factor that drives sea level rise in the future. Now, one of the most amazing things that I learned during this Climate Ready Boston initiative was how ice sheet melting is going to affect. It's not just adding water from melting ice that's going to make the effect. So let me explain this a little bit. And we've actually known about this thing called ice sheet fingerprints since the late 1800s. So this isn't anything new. So this is just a very simple schematic. Here's a big massive ice sheet, say in Antarctica. And here is the water surface if it's as we envision, it's just this spherical surface. But what happens in reality is these ice sheets are so massive, they have their own gravitational pull, and they actually pull the water that's close to them up. So the ocean surface near an ice sheet is actually higher than it should be if that ice sheet wasn't there. So the ice sheets are so massive, they pull that water up. So as those ice sheets melt, and as the shelves break off, that gravitational pull relaxes, and then the water surface actually drops near the ice sheets, which means that it sort of redistributes that water further away. So as the water surface drops near the ice sheet as they melt, the water surface actually goes up farther away from the ice sheets to correspond. That corresponds to that it's sort of a reshifting or redistribution of that water. So that it turns out that actually has a very large effect on us. That can have a very large effect on us here in Boston. So Greenland is close. So we actually would see less sea level rise due to the melting of Greenland. But Greenland's a fairly small ice sheet relative to Antarctica. When it comes to the Antarctic ice sheets, because they're far away, a relaxing of that water level in Antarctica actually causes an increase in water levels here in Boston. As the Antarctic ice sheet melts, we'd see about a 5% increase above global sea level rise here in Boston. And the West Antarctic ice sheet would actually cause 24% more sea level rise here in Boston above the global mean sea level rise that would be experienced around the planet. So here in Boston, because we're far away from these massive ice sheets that are melting, we actually see a bigger effect due to these ice sheet dynamics. So, good news, right? Yeah. Okay, so again, here are some plots of what sea level rise could look like in the future. And again, based on how we emit CO2 in the future, the answer could look very different. So if we choose a low rate of CO2 emissions, if we change to renewable energy efficiency and the like, and reduce the amount of CO2 we emit in the atmosphere, by the end of the century, we could see 2 to 3 feet of sea level rise. Still a lot, but much less than we could see. If we choose to continue on this intense rate of pumping CO2 in the atmosphere using fossil fuels and not being energy efficient, we could see anywhere from 3 to 7 feet of sea level rise in Boston here by the end of the century. That's a lot. So again, not good news in the not good news in one way, but the fact that these projections based on how our future could look are so different, it really tells us again that what we do now, the mitigation, the reducing of our carbon footprint and the reducing of our emissions into the atmosphere has a huge impact. We could reduce this impact by half if we continue to move to renewable energy and reduce our carbon footprint. So sea level rise is something we've already been seeing. Back, I don't know if any of you actually were part of the cadre of people that went out and took pictures of the king tide back in October of last year. But Boston Harbor Now actually put out a blast and said, take pictures wherever you are. So there were a lot of pictures of the king tide occurring and inundating areas that normally wouldn't be inundated, that we wouldn't have expected to be inundated, but because sea level rise is occurring, now we're getting places flooded that we wouldn't normally have seen flooded before. So we're seeing this impact. There are other places in the world, other places in the country, like down in Virginia and Norfolk, that are seeing this even a lot more. So when you live on the coast and you start seeing water encroaching on you, you actually know that this is a real phenomenon and we need to plan for it. So now that I've depressed you all, it's always depressing learning about sea level, learning about climate change. Let's talk about some good news, because there is good news to be had. So this is another New York Times article that just came out this week, stating that the U.S. has actually learned a lot from the disasters that we've experienced in the past. So the 911 disaster, which wasn't a natural disaster, but it was a disaster that pointed out the fact that government agencies really need to work together in responding to these disasters, and actually they have. Hurricane Katrina really highlighted the threat that major flooding can cause, and the damage and the destruction and the loss of life that major flooding events can cause. Hurricane Andrew in Florida in 1992 made Florida realize they needed to improve their building codes. They needed to actually build houses with the roofs tied onto the house. And so, that's how they were built. So after 1992, building codes have improved. And there was, I don't know if you saw it in the news, at one point they pointed out one house that was destroyed and then other houses that weren't, and it was because they were built with more improved building codes. So these building codes really do make a difference. After the Hurricane Allison in Houston in 1978, medical centers went through a lot of upgrades to make sure that they could respond to the patients that were coming in. And overall then, this improved response in the U.S. has caused for a dramatic reduction in the loss of life because of these disasters. The other good news, even though it's not good news that our president took us out of the Paris Agreement, as a result, 14 states created what's called the United States Climate Alliance, where they have decided they're going to continue working towards these CO2 gas, the greenhouse gas reductions consistent with the Paris Climate Accord. The city of Boston and the Commonwealth of Massachusetts are actually leaders and have been leaders for a while in climate change initiatives. So we had the Massachusetts Global Warming Solutions Act in 2008, which pledged to reduce greenhouse gases by 25% or to 25% below 1990 by 2020, and we're actually at a 21% reduction now, so that's good news. Yeah, give Massachusetts a standing O. And we're going to also pledge to reduce greenhouse gas emissions by 80% by 2050. And I swear, I was at a meeting that the governor was at on Tuesday, and I swear I heard him say that they're actually working towards carbon neutrality by 2050. And that's really amazing. So Massachusetts is really making really great strides in mitigating our impact, reducing our CO2 emissions. 205 of Massachusetts communities have adopted what's called the Building Stretch Code, and it's a more energy efficient standard that they can adopt. And so 205 out of the, I'm not sure how many there are, but a lot of communities in,
351.
Okay, so 205 out of the 251 communities, yay! Again, Massachusetts is doing great work when it comes to mitigating our impact. And the Global Warming Solutions Act actually pledged for a market transition to renewable energy as the dominant fuel by 2050. Already, there's lots of over 800 hot water solar systems since 2011, and they anticipate greenhouse gases will be reduced by 1 million metric tons by 2020. That's only a few years away. So Massachusetts is really leading the country in climate change mitigation. And speaking of electrical consumption, we have this thing called RGGI. Has anybody heard about RGGI, the Regional Greenhouse Gas Initiative? In New England here in the Northeast, we're actually the nation's first cap and trade system on CO2 emissions from the electricity industry. It started in 2009. And so what it is they come up with a regional cap of CO2 emissions, the maximum amount that we can emit, and then each state can trade those emissions, allowable emissions, based on their ability to reduce their emissions. And so it's a way of reducing overall emissions and also saving money. And so they take that money that they save from this cap and trade system, and they put it into energy efficiency of programs and reduce bills. So it started in 2009, so after 5 years they did a comprehensive overview and found that $1.37 billion in RGGI proceeds had been invested in energy efficiency and clean and renewable energy, and that they expect $5 billion in energy bill savings to nearly 5 million people, and that energy efficiency has been the major, and clean energy has been the major output from this RGGI initiative. There was a time when it looked like some states were going to pull out of RGGI. I think the program has proved that it's effective, and so RGGI has been a really positive initiative in reducing the CO2 emissions, not just of Boston or Massachusetts, but of the entire Northeast. Boston itself has a climate action plan, and it's had one since I think around 2010. It pledges also to reduce greenhouse gas emissions to 25% by 2020 and 80% by 2050, making that progress. I've put the links that you can look for the details on this. I'm sure this PowerPoint will be available to the public after this talk. Part of the climate action plan in Boston is what they're calling Greenovate Boston. So looking to make Boston not only mitigate carbon impacts, but also become more resilient to climate change impacts. So you can become a part of the Greenovate Boston initiative. Also, that Climate Ready Boston initiative that I told you about, we did the Bragg report where we came up with a consensus of what the future could look like for Boston. They took that information and then did some resiliency or some vulnerability analysis and came up with some recommendations for what Boston can do to be prepared for climate change in the future. All of this together has allowed Boston to be selected as one of the Rockefeller Foundation's 100 resilient cities. And so one of Boston's resiliency challenge is to prioritize water management while fostering social cohesion and equality. So again, you can Google 100 resilient cities Boston and you can find out more information about that. And I just wanted to tell you a little bit about what the School of the Environment is doing. We've been looking at vulnerability, social vulnerability due to climate change and infrastructure vulnerability due to climate change. One of the projects that I've been working on with my colleague is looking at how climate change is impacting low-income, vulnerable communities. East Boston being one of them. We did some mapping, saw that East Boston looked like it could have some pretty dire flooding in the future. So we met with East Boston community residents. We found out what they thought about climate change. We wanted to know how did they understand climate change. So we met with them and collected their words and then found that they understood that there are environmental impacts and that there are human aspects to climate change, and these are large-scale problems with large-scale solutions. But one thing that was missing was we didn't see how climate change would impact them individually and locally and what they could do about it. So then we had some other meetings with them, told them about some of the options for protecting. We got their feedback from what they would consider feasible options for climate change in the future. So we could put in a combination of hard structures, which is seawalls, and soft structures, which is beach nourishment, things like that. Flood-proofing buildings, but who's going to pay for it? Those kind of issues. Evacuation in a community like East Boston can be problematic because all of their family lives with them in East Boston, so where would they go? And then retreat, which is one of the options for climate change adaptation, is never a popular option. So this work has continued. It's being funded now by the Kresge Foundation, and my colleague Paul Kirshen is working with the group in East Boston and also bringing in the infrastructure and government agencies to work with the residents to work out the values and what are the options for a plan for this community. Some of the options for protection, if you put in a seawall, it doesn't have to be an ugly concrete wall. You can put it in with a viewing area. You can actually make some of your infrastructure part of that barrier, like a road, a raised road. You can nourish the beaches and build dunes as a protective barrier. You can put in landscape berms and make it part of a recreational park. Or you can do something really clever like this. And you can have what looks like a park bench, but when a flood comes, you just click it up into place and it turns into a wall. Isn't that great? So we gotta get architects and designers involved too, because they come up with all kinds of innovative ideas of how, an engineer just put up a wall. But no, we get in some architects and then we get something that's really clever like that. So you can also flood-proof existing buildings in many ways. We have lots of options, and those options are being looked at in this climate care initiative in East Boston, where residents, government officials, and the utilities and infrastructure people are all working together to come up with a plan that meets everybody's needs. This is some of the players. We got scientists, we got designers, we got community partners. Also, Massachusetts Coastal Zone Management has given the city a grant to begin actually designing a protective barrier here in East Boston and also up in Charlestown. Those are two low-lying areas that if you block the flooding there, it actually prevents a lot of flooding inland. So a lot of good stuff is actually going on in Boston to help prepare for the future of climate change. The other track that we looked at is what's the infrastructure, the impacts on infrastructure like transportation. So we worked with Mass DOT and the Federal Highway on looking at the vulnerability of the central artery. So we did some mapping back in 2010 and 2013. Mass DOT took a look at these maps and said, oh man, we got some infrastructure that's going to be impacted. So they hired us to look at what the vulnerability would be. You can imagine with this big dig now that we have running under the city, that whenever you have a portal into the tunnel, that could be, if water flows in there, that's not a good thing. We also have these big vent buildings that ventilate the tunnel. They have louvers right at ground surface, and these buildings, they go like several stories down under the building. So if we get flooding in this area and water goes in, salt water goes inside, there's big fans and lots of electrical circuits. Salt water and electricity don't get along. So there's a lot of vulnerable assets that Mass DOT and transportation has. So they hired us to look at this and try to figure out what the impacts would be. So we had to look at the causes of flooding. We've already talked about tropical storms, extratropical storms. Our partner at Woods Hole Group down in Falmouth, East Falmouth, Massachusetts, built a big fancy model that was big enough to simulate both the extratropical and the tropical storms that were coming in that would affect Boston. We made the grid for this model fine enough so you could actually have answers at all the assets that Mass DOT was interested in. And ultimately, we came up with maps that showed the probability of flooding. This was something that hadn't been done before. We had maps that showed the extent of flooding, but what's the probability? So this shows the probability of flooding in 2013, so under current conditions. So this green is around 1%. So that would be comparable to the 100-year flood. And so East Boston, the Greenway, some of South Boston, up in Charlestown, areas that have low areas that if a storm surge comes in, water could go in. By 2030, that extent increases, and also so does the probability. So this darker green is now 2 to 5% probability. And then by 2070, we'll see a lot more, a higher probability of flooding in a lot of areas. So East Boston, so this blue is around 20 to 50% probability. So you got a 50-50 chance of being flooded in any year. That's usually not considered good odds when it comes to flooding. So South Boston here, 50% probability. But one thing that also set this scenario apart was by around 2065, 2070, sea level rise may get to the point where it actually storm surge could short circuit the Charles River Dam and the Amelia Earhart dams, which were put in place to prevent water from going upstream. So then the communities behind that dam are vulnerable to flooding. So these are things that are good to know so that we can start planning. So we could have these maps. We have these maps that show individual structures, and Mass DOT can look and say, what are the probabilities of these different assets getting flooded. So also we had flood depth maps show the same thing. So there were good news and bad news for Mass DOT. The good news was that the extent of flooding under current conditions is fairly limited and the probability is fairly low. So Mass DOT has time to plan for what they're going to do. And also these regional adaptations, so blocking these small pathways, entryways for water can reduce the flooding dramatically. The bad news, of course, is some of the vulnerable structures are those tunnel entrances, and that those tunnel entrances, more of those tunnel entrances become vulnerable by 2070. So Mass DOT took this seriously. They field validated the results from the model, and now they're working on developing strategies for how they're going to prepare for this. So that just gives you a couple of ideas of the work that we've been doing at UMass Boston, specific on the ground, how we're trying to get the city and the area prepared for the potential for sea level rise and coastal flooding. So I know you've been listening to me. You've been very patient listening to me for a long time. I just wanted to sort of bring this all to a conclusion. So the things we know about climate change. We know that the greenhouse gases that we've emitted into the atmosphere have been the major cause for the warming that we've observed since the late 1800s. We know that small changes in those mean values can have larger impacts on the extremes, so we can expect to see more extreme events in the future. We know that reducing our greenhouse gas emissions will really have large impacts on how the climate looks later in the century. Right now, not so much, but later in the century, we can have big impacts on, big effects on how much climate change we see. We also know that the emissions that we've already put in the atmosphere has embedded a certain amount of change in the climate, so we know we have to adapt. And we know that if we ignore all of this change in climate stuff, that whatever we plan or design in the future is just going to be wrong. So we have to take it seriously, we have to understand it, and we have to plan for it. So what is the role of climate change in these disasters that we've seen recently? Well, extreme events will always happen, and under a changing climate, they're going to happen more frequently, and they're going to be more powerful. For those we've already experienced, climate change is essentially like pouring salt into a large wound that we've already created for ourselves. We've put ourselves in vulnerable places. We've paved over paradise and put up a parking lot, no place for the water to go. We've got lots of flooding because of the policies that we've basically, agreed to over this time. So we have to understand that. But in the future, I view climate change as sort of the 800-pound gorilla in the room that's forcing us now to do the things that we know we should have always been doing along the way. For example, floodplain and coastal development. We know that if you live near a river or the ocean, you're likely to get wet. So now that we know that the likelihood of that is going to even increase because of climate change, we really need to think more clearly about how we want to deal with floodplain development and coastal development. We know we have a lot of social and economic inequity, especially here in Boston, being one of the most inequitable cities in the country. Well, we also know, big surprise, that the most vulnerable people to climate change are those low-income people that are in these highly vulnerable areas. So we know if we deal with the social inequity issues, we'll also help take care of this social vulnerability issue as well. We know we should have been sustainably and sanely developing over time all along. We just were kind of hoping we could get away with it, right? Well, we have, but now we have a decision to make. Do we just want to stay where we're at and just plan on getting flooded regularly and pick up after it? Or do we as a society want to decide that we have to change our policies about how we develop, where we develop, and the kind of development we have? Energy use and policy. We know that we can be more efficient, and we are making strides in being more efficient and having more efficient policies, and that will impact climate change as well. The more efficient we get in energy, the more we use renewable energy, the less climate change impacts we'll have in the future. So we've made a lot of progress on these so-called low-hanging fruits. We're more energy efficient. We're starting to put in pervious pavement and low-impact development kind of initiatives that can help reduce the amount of flooding in areas when we get these extreme events. But we still have a lot of hard decisions to make. What are we going to do about all those people that are living in these vulnerable areas? That's a choice we're going to have to think about. Are we just going to say, all right, you're going to get flooded and we'll just help you, recover every time it happens? Or do we start deciding that we need to reserve areas for water so that it doesn't cause impacts? These are hard decisions. What are we going to do about subsidizing flood insurance? Actually, subsidizing flood insurance has actually created the ability for people to move into these vulnerable cities. Are we going to continue that kind of policy? These are really hard decisions that we have to make as a society. So I don't have the answers. I hope you do. And we've got a lot of students here that are going to have to deal with these issues in the future and really have to face these hard decisions head on. So I guess that's all I wanted to say about that. So now we can take some questions. Yes.
Hello, my name is Chris Meyer. I work for Boston University's Institute for Sustainable Energy on the Carbon Free Boston project.
Great. Yeah.
And I just wanted to mention that one of our senators, Mike Barrett, has proposed a bill that would enable a checkbox option on the Massachusetts state return so that people can contribute to the Least Developed Countries Fund. That's part of UN. And that would enable people to contribute, and there's 48 of the poorest countries are involved, and that's to help them adapt to climate change. So if you're interested, go to change.org, and they'll show you ways to help to get this passed. Okay.
All right.
Thank you.
So I guess we have a time for a couple of questions. So the question is how melting permafrost and the release of methane could affect climate change impacts. So are you talking about the Boston results or just overall?
Overall.
Yeah, so I'm no expert on methane, but I do know that methane release is one of those feedback mechanisms that is not always well understood in the climate model. So you get warming, you get a melting of the permafrost, which then releases methane that's in the soil, which then accelerates the warming, which then accelerates the methane release. And so it's probably not good news, but that's about all I can say. What are the ethical obligations of engineers to account for climate change in their designs? Well, that's a really good question. And it turns out, so I'm an engineer, and so engineers, the one thing that we think about most, I think, when we're designing things is we don't want to cause a loss of life, and we don't want to get sued. And so, one of the things that is big in engineering is this thing called loss prevention, which is, and so engineering over time has developed this expertise, this experience, and so there's these standards of practice that engineers follow to try to reduce that loss of life potential and also to reduce the liability. So used to be you didn't want to venture outside of that standard practice, but now it turns out that climate change is so compelling that many engineers are actually working to incorporate. They're looking at the long-term projections and incorporating these projections into their designs, at least considering the impacts of what if you design to a bigger 100-year storm as opposed to the standard 100-year storm. And it's becoming now part of the loss prevention protocol to actually include climate change as a consideration. So we've sort of shifted from we just want to do it the way we've always done it because then we won't get sued, to we're going to include things that we know are occurring because we're afraid we might, we don't want to cause a loss of life or get sued because we didn't include climate change. So that's a good news. Yes. Yeah, I'm a hydrologist. That's a really tough question. So that's more, regulations and policy. So the housing industry has a very short time frame of interest. You build a house, you sell a house, you don't worry about it anymore. So you have to actually have the state and local governments pass ordinances and regulations that force them to consider those kinds of things. That's about all I can say about that. Yes, one more question? Okay.
Yeah, hydrology there.
Yeah, so the question is, so I presented a lot of stuff on the coast. What about inland hydrology and what about the impacts of extreme weather events? I know, yes, people are worried about that too. They're looking at how the so-called the design storms, the 100-year storm, the 25-year storm, how those are going to be impacted by climate change, and then changing our designs based on those higher numbers. And certainly when Hurricane Irene came through in 2011 and devastated a lot of Vermont, that really brought to light that whole inland flooding and the extreme event impacts on inland rivers and inland infrastructure. So that's a big area of investigation and design as well. So I guess is that, sorry. Yes, one more.
Can I say something?
Yes, of course.
Excuse me. Sorry, as one of the sponsors of this, Helen Waldorf, Boston League of Women Voters. But I'd like to say, the League of Women Voters is the oldest nonpartisan group in the country, period. We've been working on nonpartisan issues. And the point I wanted to make is that climate change is not a partisan issue. It has been made partisan. No, wait. It has been made partisan by both sides of the House. I blame both sides of the House for this, and you know who I'm talking about. It's not a partisan issue. So if you want to work on climate change, get everybody you know to vote, whoever they're going to vote for, because that will solve the problem eventually. That's all I have to say.
And on that note,
Thank you, Dr. Douglas. And on behalf of the League of Women Voters in Massachusetts and New England Aquarium, thank you for being here tonight. Fantastic lecture. I really very much enjoyed it.